Good morning, students. My voice is audible, and can you see my screen? Good morning, students. My voice is audible. Can you see my screen? Can you respond?
Yes, sir.
Okay, fine. So let me wait for a few other participants, and then I'll start the session. Meanwhile, students, just you can go to this bitwise operators, right? Probably in my previous class, I have not discussed this bitwise operators. So in today's class, I'll be discussing this bitwise operators. Yeah. Okay, so let me start the session. In today's class, we are going to discuss about this bitwise operators, right? So bitwise operators. So now what is this bitwise? Means all these operators, you can see there are several operators out there. All these operators, okay, is going to operate on bits. Okay. All these operators is going to operate on bits. What's a bit? 0 is a bit, 1 is a bit, right? 0, 1, 0, 1, 1. So this everything is a bit, okay? In order to perform operation on these bits, in order to perform operation on these bits, we are going to use the corresponding operators. Using these operators which are listed here, okay? I'm going to perform operation on these bits. So therefore, we call this as a bitwise operators. So using these operators, what I can do, I can perform operations on this bits, okay? A bit is nothing but it can be either 0 or it can be either 1. A bit can be either 0 or it can be either 1, right? So now let us see these bitwise operators in detail. Okay, so let me clear my drawings. And before the students, now how to identify, for example, let us assume written a number 0, 1, 1, 0, 1. So what's the value of this? This is a binary number, right? So how to convert this in decimal value? What's the corresponding decimal value for this binary number? For the decimal students, decimal value? Yeah, students, my voice is audible. And can you see my screen? Yeah, fine. Okay, fine. Now, see that. So let me write the corresponding number 10101. Okay, this is a binary value, right? So this is a binary value. And what's the corresponding decimal value for this binary value? What's the corresponding decimal value? What's the corresponding decimal value? What's the decimal value? So how to compute, students? So in order to compute, we're going to use, so there's 1, right? So we'll do 2 power 0. This is 2 power 1. This is 2 square. This is 2 square. And this is 2 cube. This is 2 cube. And this is 2 power 4. This is 2 power 4. Now what's the value of 2 power 0? It is 1. What's the value of 2 power 1? It is 2. What's the value of 2 power 2 square? It is 4. And what's the value of this 2 cube? It is 8. And what's the value of 2 power 4? It is 16. Okay. Now, in order to compute the decimal value, what I'll do? I'll do 1 into 1. So 1 into 1 is 1 plus. Okay. Next, 2 into 0. 2 into 0 is 0. Anything multiplied by 0 is 0. Next, 4 into 1. 4 into 1 is 4 plus 4 plus. Next, what I'll do? 8 into 0. 8 into 0 is 0. So 16 into 1. 16 into 1 is 16. That is 16. 16 plus 4 is 20. That is 21. So the corresponding decimal number with respect to this binary value is 21. So like this, you're going to compute. So once you have a binary value, that binary value you can convert to corresponding decimal number. So for example, I want to find, let us assume I want to find 35. So for decimal number 35, I want to find the corresponding binary number. For a decimal value 35, I need to identify the corresponding binary value. How we can do it? It's quite simple. So let me write 1, 2, 4, 8, 16, 16, 16, right, students? 32, right? 32. That's the 35. So now I need to get 35, right? So put 1 here. So I got 32. 32. 32 plus 4, I won't get 32. 32. 32 plus 2, how much you'll get, students? 32 plus 2 is 34 plus 1, 35. The remaining everything you put 0. 0, 0, 0. And that's it. So this is the corresponding binary value for this decimal number. That's very simple. Now, how I got this? The same thing, similar fashion. 2 power 4 is 16. And next I'll write 2 power 5. What's the value of 2 power 5? 2 power 5 is nothing but is 32. Next is 2 power 6. So like this it goes on. 2 power 6 is 64. 2 power 6 is 64. Similarly, I'll get 2 power 7. What's the 2 power 7? 2 power 7 is 128. Next is 2 power 8. What's the value of 2 power 8? 2 power 8 is nothing but is 256. Like this it goes on. You can compute that. Right? I hope you understood how to compute a binary value from a given decimal number. If you give a decimal number something like this, you can compute a binary value like this, right? Clear my drawings? Yeah. So let us discuss. You can see that. There's some points are there, just you can go to these points. So these bitwise operations we can perform on integer types. Okay, these bitwise operations we can perform on integer types. What are integer types? That is long, int, short, char, and byte. On all these types, that is long, int, short, char, and byte, what I can do, I can perform this bitwise operations. Okay, all integer types, but except character, are signed integers. What do you mean by signed integers? For example, 42 is a number. 42 is a number, but this 42 I can put a sign. I can put a sign. So we call this as sign. Okay. So that's what it says. That's what it is, sign. We call it signed integer. Minus 42 is a signed integer. Why? You can see that I have a sign called negative. Okay. So this signed integers is possible with respect to long, with respect to int, with respect to short, with respect to byte, but with respect to character, we can't have a signed integer. So what I mean to say that, for example, I written a variable called, I can write it something like this. Int equal to minus 32. I can do, sorry, int a, sorry, int a equal to, I can write int a equal to minus 32. Similarly, I can write it byte. I can write it byte a equal to minus 10. So see that, students, that's what it says. So with respect to integer and byte, what I can have a signed number. So the negative value indicates it's a signed number. Is it right, students? It is a signed number. 1 second, students. Yeah, fine, students, right? Yeah, I hope you understood what is this sign. So similarly, I can do for long. Similarly, for long also, what I can do, I can have a signed number. But with respect to character, we can't have a signed integer. Okay, so minus 10 is a signed integer, minus 32 is a signed integer, and that's what it says, right? Yeah. All integer types are represented by binary numbers. All integer types are represented by binary numbers of varying bit widths. What it means, all integer types. For example, I'll write byte. I'll write byte a equal to 10. Okay. Now I need to represent this 10. How we can represent this 10? Let me put it 1, 2, 4, 8. Okay, so I'll put 1 here. 1 here, 2, 1. So for 8 plus 2 is 10. So remaining what I'll do, I'll put 0, 0. It is a binary number. Now here you see that A is of type byte. As you know that byte is going to occupy 8 bits. Byte is going to occupy 8 bits. Is that right? Byte is going to occupy 8 bits. So here how many bits are there? 1, 2, 3, 4. Now what should I? 5, 6, 7, 8. Is it right? The entire remaining bits, what I can do, I can put it as 0. Right? So like this, we can represent something like this. 1, 2, 3, 4, 5, 6, 7, 8. Why I represent using 8 bits? Because byte is going to occupy 8 bits. So that's why using 8 bits, I have represented this number called 10. The same thing, let us assume I have done something like this. Int a equal to 10. I have done int a equal to 10. Now integer is going to occupy how many bits? Integer is going to occupy 32 bits. It's going to occupy 32 bits, right? So now it's going to occupy 32 bits. Now the same integer, now what I should do, I should represent in terms of 32 bits. So what I should do, I should extend this. I should extend this box. So I should write it right. I should go up to. So it should be, count should be 32. So start from the 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. So it goes up to 32. So total size of the bits should be 32 bits. I hope you understood this, right? Why you have taken here 8 bits. So why you have taken here 8 bits? Because byte is going to occupy 8 bits. That's why I have drawn in terms of 8 bits. The same thing, if 32 bits is there, what I should do? I have to put 0, 0, 0, 0, 0, 0, 0. Up to 32 bits, I have to put 0. Why? Because int is going to occupy 32 bits. So with respect to int a, I should represent the number in 32 bits. So that's what it says. All integer types are represented by binary numbers. All integer types are represented with binary numbers. Varying bit widths. Varying bit widths. What is varying bit widths? With respect to byte, I will represent, that is byte A. With respect to byte, I will represent the same term number using 8 bits. Using 8 bits, I will represent it. Now the same number with respect to integer, I will represent it using 32 bits. The same term number. That's what it says. You see that? Varying bits. So you see that the bits is varying here. Here you have used 8 bits, but whereas here I've used 32 bits. Okay, it depends upon the type of your variable. Okay, I hope you understood this. Now these operators acts upon individual bits. This operator acts upon individual. What is these operators? All these operators acts upon individual bits. That is, suppose 1, 0, 1, 0. Okay. So all these operators is going to act upon individual bits. This individual bit, this individual bit, this individual bit, this individual bit. Okay. Using these operators, what I can do, I can perform operation on this individual bits. The most important, I'm not performing operation together. And all the bits together, I'm not going to perform the operation. But what I'm trying to do, I'm trying to perform operation on this individual bits. And that's what it's very, very important. Okay. Using this bitwise operators, what we're going to do, we're going to perform operations on individual bits. Is it right, students? Fine. So let me clear my drawings now. You can see some example, which is very important, right? So you see that 42 is a integer number. How to represent in binary value? So this, so you can represent in binary value. I think just now discussed, right? How to get it? This is 2 power 0. This is 2 power 1. That is 2. This is 4. This is 8. This is 16. And this is 32. Right? 32 plus 8 is 40. And 40 plus 2 is 42. So therefore, this is the corresponding binary value for this number called 42. Is that right, students? Next. Next, minus 42. So how to represent minus 42? So 42, you represent something like this, but how to represent minus 42? So in order to represent minus 42, we should represent minus and negative values in 2's complement. Any negative value, we should always represent in 2's complement. That's very, very important. Why you are taking 2's complement? But because you see that it's a negative value. So any negative value must be represented using 2's complement, right? So how to represent a number, a negative number in 2's complement? Let us see. So in order to represent a number in 2's complement, these are the three important steps which we need to follow. So first, what we need to find the binary value of a number, and next what we should do, we need to change ones to zeros, and we need to change zeros to one. That is your second step. And the third step is finally what we should do, we need to add one to the result. So let us illustrate this with a small example. So let us take the same number called minus 42. So now this minus 42, I want to represent in binary numbers. In order to do that, what I should do, step one, what I should do, I need to find the binary value of 42. And what's the binary value of 42? This is the binary value of 42, and just now we came to know. Now what I should do, the second step says that I need to change ones to zeros and zero to ones. So that's what I've done. You see that the zero has been changed to one, and one has been changed to zero, zero has been changed to one has been changed to zero, zero has been changed to one has been changed to zero, zero has been changed to one, and zero has been changed to one. And that's what the second step says, right? Next, what it says, I need to add one to the result. Okay, so let us try to add one to the result now. So once I add one to the result, so you see that for this, so one after converting, I got this number, right? For this number, for this binary value, what I should do, I need to add a one. So once I add one plus one, what I'll get, students? So once I got one plus one plus one is nothing but it is 1 0. So when I do 1 plus 1, I'll get 1 0. So this 0 will go here. You see that this 0 will go here, and this 1 will go as a carry. This 1 will go as a carry. Now I'll do 1 plus 0. 1 plus 0 is nothing but it is 1. Okay. 1 plus 0. See, 1 plus 0 is nothing but it is 1. And similarly, here nothing is there. So directly 1 will come. Here 0 will come. Here 1 will come. Here 0 will come. Here 1 will come. Here 1 will come. Okay. This is the result. Okay, this is the result. So what is this? This is nothing but we call this entire number as minus 42. Now the most important thing here is, so see here we call this as higher order bit. See, what is this? This is a negative number. Okay, this is a negative number. So for negative numbers, the higher order bit will always have the value called 1. See that? For a negative, this is minus 42. Okay, for all negative numbers, the higher order bit. What is higher order bit? Is the last bit. Is the last bit. We call this as an higher order bit or MSB. We call this as MSB or higher order bit. MSB stands for most significant bit. For a negative numbers, the MSB will be always 1. Okay, but you see that here, this is also 42. Yes, that's what initially what you have done. You see that initially find the binary value of 42. This is plus 42. See, since it's a plus 42, you see that the most significant, that MSB is 0 here. You notice it is 0 here. Whereas for minus 42, you see that it is 1. So by seeing this most significant bit, that is higher order bit, we can easily make it out whether it is a positive number or a negative number. Okay. Now, let me clear my drawings. Now let us assume that they are given this binary number. They are given this binary number. Now from this binary number, I want to find out the corresponding decimal value, right? So by seeing this one, I know that it is a negative number. Okay. So how to decode? So how to decode a negative value? So in order to decode, how we can do it? These are the steps we need to follow. How to decode a negative number, right? So in order to decode a negative number, first what we should do, we need to invert all of the bits. Inverting is nothing but I need to change 0 to 1, and I need to change 1 to 0. That's what it is, inverting. Okay, that's what it's inverting. So now you see that I've inverted all the bits. So initially what is there? It is 0 is there. So therefore inverted to 1. So here what is there? Here 1 is there. So 1 have changed to 0. And next 1 is there. So 1 has changed to 0. And 0 is there. Next 0 has changed to 1. Next 1 is there. 1 have changed to 0. Next 0 is there. 0 has changed to 1. Next 1 is there. 1 have changed to 0. And again 1 is there. 1 have changed to 0. That we call it as inverting. So invert all the bits. So after inverting all the bits, what I should do? So I got a value called 41. So once I invert all these things, I'll get a value called 41. So how will you get a value called 41? Here 1 is there. 1 means 1, 2, 4, 8, 8, 16, 32. This one is 32. 32 plus 8, how much? It is 40. 40 plus 1 is 41. So therefore, I got 41. Next, what I should do for this 41? I need to add 1. So once I add a 1, I'll get a number called 42. I got a number called 42. So since I have since in higher order bit I have 1, we call this as minus 42. So like this, we can decode. Like this, we can decode a binary number which is having a 1 value at the higher order bit. Yeah, fine. So that's all. Any questions, students? These operators? Any questions? No questions? Well and good. So let us move to this logical operators, right? So what is this logical operators? So there are, we call this as bitwise operators, bitwise logical operators. What are bitwise logical operators? This AND, or, XOR, NOT. So to be more specific, we call this as bitwise AND. We call this as, actually this naming you can see in the first slide. Let me move to the first slide. Better start doing something like this. So that everyone the names. See that you can see the names. Okay. See every symbol we have a name. For this symbol, what's the name of this? The name of this is nothing but it is bitwise AND. For this symbol, what's the name? This bitwise OR. For this symbol, what is this? Bitwise exclusive or we can call it XOR. Okay, bitwise XOR, or something we'll call it, right? That's what it is. There's a naming you can see in the first chart. Okay. Yeah. So now let us try to analyze this. Okay. So this is so let us see about this is R. R. So with respect to R, okay, with respect to R, if at least one bit is true, so I'll be considering one as true. I'll be telling one as true. I'll be telling one as true. I'll be telling zero as false. So I'll be discussing one as true and zero as false. Okay. So with respect to R, if at least one bit is true, the output will be true. You see that the both are false, so that's why the output is false. That's why I got 0. But you see that here A is 2, that is A is 1, therefore the output is 1. But here you see that B is 1, B is 1, but whereas A is 0. Since at least one is true, the output is true. But here you see that the both are true. Since both are true, the output also will be true. This is true with respect to R, right? Now let us move with respect to N. With respect to N, both inputs should be true. Okay, you see that here, this is false, and therefore it is false. But you see that A is true, but what about B? B is false, therefore the output will be false. With respect to N, both should be true, then only output will be true. Here you see that A is true, whereas B is false, so therefore the output is false. But you see that in the last case, both are true, that is A is true and B is true, and therefore the output is true, right? That's what you should know. Now, with respect to XOR, we call this as XOR. With respect to XOR, only one input should be true. With respect to XOR, only one input should be true, then only output will be true. You do see that here, the both inputs are 0. Since both inputs are 0, the output is 0. And you see that here, the both inputs are 1. So therefore, the output is 0. So when it will be true, it will be true only if only one input is true. Here you see that A is 2, whereas B is false, and therefore the output is 1. But here you see that A is false, but whereas B is 2. Here only one input is true, so therefore the output is true. And that's what it is, XOR. Okay, yeah, fine. Now let us see about this negation. What is this negation? This one is nothing but I'm trying to invert the bits. Here 0 is there. Negation of A is nothing but is 1. So here 1 is there, but inversion of 1 is 0. I'm inverting the bits. Here 0 is there. I'm inverting 0 to 1. Here 1 is there. I'm inverting to 0. Right? That's what it is. And the most important, I have discussed this, all these operations, all these bitwise operators we have discussed here is going to operate on individual bits. It's going to operate on individual bits. Now let us see this with an example. Bitwise not. Okay. So what not is nothing, I'll be calling sometimes as negation, not. So what is the binary value of 42? So in order to compute the binary value of 42, you see that this is a binary value of 42, right? This is a binary value of 42. Now I want to compute bitwise not. How to compute bitwise not? Not is nothing but I need to negate. That is, I should change from 0 to 1 and 1 to 0. And that is what bitwise not is all about, right? You see that? I've done it. So you can see that 0, 0 I've changed to 1, and 1 I've changed to 0, and 0 I've changed to 1. As you see the students, I'm trying to perform operations on individual bits. So you see that 1 I've changed to 0, I've changed 0 to 1, and I've changed 1 to 0, and I've changed 0 to 1, I've changed 0 to 1. You see the students, I'm trying to perform operations on individual bits. Is it right, students? Yeah, fine. And similarly, how we can do this one? So in order to convert this, how to convert this? Here 1 is there, so 1 I should change to 0, and this 1 again I should change to 0. Again this 1 I should change to 0. Again this 1 I should change to 0. Again this 0 I should change to 1, and this 0 I should change to 1. This 0 I should change to 1. This 0 I need to change to 1. So this is bitwise not operation on this 15. Okay, that's what it is. The right, student? Yeah. Now let us try to perform bitwise end. Okay, now let us try to perform bitwise end. So what we discussed bitwise end. End means the both inputs should be true. You can take this as A, you can take this as A, and you can take this as B. Okay. If both inputs are true, then only output will be true. That is A should be, that is A should be 1 and B should be 1. So then only my output will be 1. Otherwise it will be 0. Is it right, students? And now let us see that operation. You see that I got the output. You see that both A and B both are 1. So therefore I'm getting output as 1. Here also you see that both A and B are 1. Therefore I got output as 1. Right? But remaining all cases you can see that I got an output called 0. Right? That's what it is, bitwise end. Okay. Now let us move to next operation, that is bitwise OR. Okay. So with respect to bitwise OR, we have seen what is bitwise OR. If let us assume this as A and this as B, the same thing. With respect to bitwise OR, if at least one input is true, the output will be true. Okay. So here A is 1 and B is 0, the output will be 1. And similarly, if A is 0 and B is 1, the output will be 1. So at least one input is true, the output will be true, right? So let us see here, and you see that, students, I got the output. You see that in all these cases, you see that in this case both inputs are 0 0. So therefore I got 0 0. You see that here also I got the output called 0 0. Why? The both inputs are 0, but remaining all cases I got 1 1 1. Okay, because at least one input is true, that is 1. Okay, yeah, fine. Now let us perform. Now let us do XOR operation. What is XOR operation? With respect to XOR operation, let us consider this as A and let us consider this as B. Right? So with respect to XOR operation, we have two inputs, A and B. A and B. So when the output will be true, if A is 0 and B is 1, the output will be 1. If A is 1 and B is 0, the output will be 1. For remaining cases, that is 0 0 and 1 1. For these two cases, the output will be 0. Right? So that's what it is. So now let me run the program. Yeah. You see the students, I got the output. So in which case the output is 1? You can see that for this case it is 1, and for this case it is 1, and for this case it is 1. See that? At least only one input should be true. Then only output will be true. For remaining all cases, you see that in these cases, you see that both inputs are 0. And you see that here also both inputs are 1. Okay, so therefore the output is false. Output is false. Is it right, students? I hope you understood this. That is bitwise XOR operations, right? And the most important here is it. I said that we are going to perform operations on individual bits. You see that I have taken this bit and I have taken this bit. You see that I have taken this bit, I have taken this bit. I'm trying to perform this XOR operation. And what's the output I got? I got output called 1. In the next, again, I've taken this bit and I've taken this bit and then perform XOR operation, and I got output called 0. So therefore, using these operators, what we can do, we can perform operations on individual bits, right? Yeah, fine. And next is this left shift operator. Okay, this is quite interesting. What is this left shift operator? Okay, now, so this is your left hand, this is your right hand, this is your left hand, this is your right hand. Okay, We call this as less than symbol. We call this as less than symbol. Now if I write one more less than symbol, we call this as left shift. You see that this is pointing towards left side. This is pointing towards left side, and therefore we can make it as this as a left shift. Just I am telling for you to understand. Okay, you see that this pointing, it is a pointer, this is pointing towards left side, so therefore we call this as a left shift operator. The parallel to left shift, we have a right shift. So this is greater than symbol, and let me write one more greater than symbol. You see that now where it is pointing towards right, and we call this as right shift operator. We call this as right shift, and whereas we call this as left shift operator, right? Now let us discuss these operators in detail. So this is the general form of this left shift operator. Okay, here we'll give some value, and we're going to ask for, here we are asking for left shift. Now how many times I need to perform left shift? This number dictates how many times I need to perform this left shift operation. Anyhow, let us discuss in detail with a small example. Okay, fine. With a small example program, right? Is the output of this program. Yeah, let me discuss this. It's very, very good program. It's very, very best program, best code. Now here you see the students here. So here I've done byte a equal to 64. Okay. So I've taken a variable called a. I've taken a variable called a. Inside this variable called a, I'm trying to store a value called 64. And what's the type of a? The type of a is byte. Okay. So now let me represent the value 64 in binary value. So what's the binary value of 64? The binary value of 64 is nothing but this is a binary value of 64. Okay. So why here I've taken 8 bits? Why I've taken 8 bits? Because you see that the a is of type byte. As you know that byte is going to occupy 8 bits. Since byte is going to occupy 8 bits, the number 64 are represented using 8 bits. Right? That's the intention. Now, and you see that here. Okay. Now here, the same variable called a. What is a? A is of type byte. Now this a I'm trying to use in expression. Is an expression. What is an expression? A plus 2 is an expression. Okay. Similarly, any operator, we call this as a left shift operator. Okay. So now I think in the previous class I've discussed about type promotion. Okay. What is a? A is a byte. When you're trying to use a byte variable expression, okay, this variable a will be automatically promoted to int. I've discussed this. We call this as type promotion. We call this as type promotion. When you try to use any byte variable, a is a byte. When you're trying to use any byte variable in an expression, automatically it gets promoted to int type. So therefore, the entire result will be of type int. The entire result will be of type int, and this int, what I should do, I need to store in a int variable. Since the entire result is integer type, and therefore the result also I need to store in an integer variable. You see the students, and that's why here they are storing the value in I. And what's the type of I? The type of I is nothing but is int. Okay, here also, since I'm trying to use this byte variable a in expression, it is automatically promoted to int. Is automatically promoted to int. Now, since it is promoted to int, the same binding number I need to express in terms of 32 bits. Is 8 bits. Since integer occupies 32 bits, now the same binding number I'll be expressing in terms of 32 bits, right? So you can see that. I see that everything remains same. You see that? So you see that here. Here I'm having 1. Okay, so 1. So same 1. See that same thing. But now this everything is a 32 bits. So remaining all bits, that's what I've discussed. Remaining all bits, you see that I've set to 0. Why you have set 32 bits? Because type promotion takes place. When you use a byte variable in an expression, automatically the byte will be promoted to int. Therefore, I've expressed the same 8 bits into 32 bits. Is it right, students? Yeah, let me clear my points. Now, listen very carefully. Now here you see that I'm trying to print the value of a. And next what I'm trying to do, I'm trying to print the value of I, and I'm trying to print the value of b. Now what's the value of a? Initially the value of a is 64, so therefore I got output as 64. Next I'm trying to print the value of I. So what I got the value of I got the value of I as 256, whereas I got the value of b is equal to 0. Why I got it? Let us see. Now here you see the students. I'm trying to perform what I'm trying to do. I'm trying to perform left shift 2 times. I need to perform left shift 2 times. What is left shift? This is left This is left, this is right. Means I need to shift the bits towards my left. I need to shift the bits towards the left, right? Now this is my original bits. Now I need to perform left shift two times. I need to perform left shift two times. Now what I'll be doing? You see that now I'll be doing first left shift. See that I've shifted. You notice what I've done? I shifted this bit towards this side. Means I need to shift towards left. That's what left. And you see that this last bit will be lost. I've shifted towards left. This last bit is lost. Since I've shifted here, so this cell is vacant. This cell is vacant. And this cell is vacant. What we should do? We need to fill this cell with the previous value. What's the previous value is there? Since the previous value 0 is there, I'm going to fill with 0. You see that here, this one has been shifted towards left. I've shifted towards left. And since I've shifted towards left, you see that the one has moved here. One bit it has moved. Initially it is here. I moved one bit towards the left. This is my first shift. But how many times I need to shift? I need to shift two times. So right now I've shifted one time. So let us try to perform the shift one more time. I need to perform shift for one more time. So here the value 0 is there, and that's what I said. So now I need to perform what I should do. I need to perform the second shift. So I've done the first shift. Now what I should do? Now I need to perform the second shift, second time. So again, what I should do? I'm going to move the 0 to here. Since I moved the 0 to here, the cell is vacant. And you see that here is 1. I moved it to here. I moved it to here. And therefore, the 1 is present here. So I perform two shifts. So that's what it says. That's what I said. This number dictates. This number dictates how many times I need to perform this left shift operation. Since the number here is 2, I'm trying to perform left shift. How many times? Two times. I'm going to perform two times. Where is two times? This is my first time. This is my second time. And what value I need to fill here? Previously I have a 0 value. So here also I need to fill a 0 value. Right? I need to fill a 0 value. Right? Now here you see that what I'm trying to do, I'm trying to print the value of I. I'm trying to print the value of I. And what is the value of I? It is 256, right? The result I'm storing in I. And what's the type of I? The type of I is int. Since the type of I is int is going to occupy how many bits? The int is going to occupy 32 bits, right, students? The int is going to occupy 32 bits. Now, what is the number of this? So I need to convert to corresponding decimal number. So this binary number, I need to convert to corresponding decimal number. So how to convert? This is 1, this is 2, this is 4, this is 8, this is 16, this is 32, this is 64, this is 128, this is 256. I got 256. So therefore, you see that the value of I is 256. The value of I is 256. Now, with respect to I, I'm going to consider 32 bits. With respect to I, I'm going to consider 32 bits. Why 32 bits? Because I is of type integer. Since is of type integer, I have to consider this as my 32 bits. Is it right, students? Yeah, fine. Now let me claim my drawings. Now you see that here, as I said, there's this entire result. This entire result is an integer. This entire result is an integer. Now this integer, what I'm trying to do, this integer, I'm trying to convert back to byte. This integer, what I'm trying to, and converting back to byte, right? And therefore, a result I'm storing in a variable called b. And what's the type of b? The type of b is nothing but is byte. I think we call this as typecasting. Probably you must have studied typecasting in C programming. We call this as typecasting. We call this as typecasting. What is typecasting? You're changing from one type to another type. Actually, the result is int. Result is int. This result in what I'm trying to do, I'm trying to typecast. I'm trying to cast to byte. In order to cast to byte, I'm writing byte. And therefore, since I've casted, I'm going to store in a variable called a, and the type of variable